Hello, welcome to the NetConf tutorial. In this module, we'll be doing a detailed technical tutorial of the NetConf Network Management Protocol. From this module, you'll learn a very detailed understanding of the capabilities of the protocol and how it operates. So, first off, NetConf transport. NetConf messages are encoded as XML. This protocol, if you took a dump with it with a protocol sniffer and took a look at it, you'd see it's actually human readable XML, and you'll be able to actually see the protocol working. In fact, in a good portion of this module, we'll look at some actual protocol traces of actual use cases to illustrate how the protocol works. NetConf exists as both 1.0 and 1.1 versions. We'll see when the client and server connect to each other, they negotiate capabilities and agree on which version to work with. In NetConf 1.0, each message was framed by this character sequence of square brackets and greater than signs that you see to indicate a break between the XML packets. In NetConf 1.1, changed the encoding slightly so that there's a line with the number of characters to read in ASCII. So in other words, it's run length encoded basically. In terms of transport, that NetConf XML is then carried on typically an SSH on top of TCP. There are RFCs for carrying NetConf over SOAP, BEEP, and TLS. However, in the real world, these really aren't used. SSH is pretty much what everybody carries NetConf traffic on, so to interoperate, your network device should use NetConf over SSH. SSH provides authentication, integrity, and confidentiality of the traffic. In other words, it secures the traffic. That SSH is, of course, carried over the TCP protocol. So TCP gives us streaming and reliability for efficient use of the connection. Since it's a reliable protocol, the manager knows that the message got to the device. It doesn't need to read back or check anything like that. NetConf is extensible. There is a core set of NetConf operations specified in the RFCs that cause the core pieces of the operation. However, it was designed from the outset for extensions, so you could add new operations as we learned, how the protocol should be extended, what new operations could be useful. So we need some way to know where or what capabilities these devices have. The NetConf management station, in technical terms, is the NetConf client, and in the network device is the NetConf server. Oftentimes people will say NetConf manager and agent, but technically client is the manager, server is the device. When the connection first is initiated, once things have authenticated, both the client and the server will simultaneously send hello messages, in which is a list of capabilities of the device, and in there we'll identify versions of the NetConf protocol specified, any extensions, along with data models. We'll see full examples of this later when we look at some trace. In particular, it's the network device's capabilities that are needed to be known by the manager to know what to speak or how it can speak to it. It also identifies, as I said, the data models. So the management station, when it connects to the NetConf device, automatically knows what data models and also revisions of those data models are present in the device. There's no guessing. NetConf also defines the idea of configuration data stores in the device. There are defined in the RFCs the concepts of startup, running, and candidate. These data stores could be turned on in various capabilities. The running data store reflects the current running configuration in the device. If startup is present, startup is a persistent data store of configuration that reflects the startup configuration of the device. In ConfD, what will happen if you have startup and running going, when ConfD starts up, it will take the contents of the startup data store and copy it to the running data store and this will be the configuration then the device starts with. If a device only has running, that is both its running and startup configuration in that data store. Another common configuration of data stores is to have candidate and running turned on. Candidate is a future candidate configuration for the device. It is not live on the device isn't using it, it's just a persistent potential future configuration. You'll see later that you can commit candidate into running, meaning contents of candidate become the contents of running in the new running configuration. So with candidate, you can set up various configuration that you may want and then transactionally commit it all into running. So running is mandatory. Startup and candidate are both optional. It will be advertised by the device and its capabilities in that hello message to say whether it has startup or candidate available for the manager to use. Also, there's the concept of the running data store. Is it directly writable? If you have running and candidate turned on, can running only be written to via candidate? In other words, write to candidate, commit to running, or can you also write directly to running? These, when we see with ConfD, we'll see later in a subsequent module on how to actually work with configuring and using the NetConf server in ConfD, that there's various options you can set for selecting candidate, startup, whether running is writable, etc. The important thing to understand right now are there's these three data stores that are possible in the basic function of each. NetConf is inherently a transactional protocol. It's designed from the ground up for doing transactional configuration of a device or a network-wide transaction of devices. So typically, the EditConfig operation is used to do a configuration change to a device in NetConf. That EditConfig can be going to the running data store directly. An EditConfig is effectively one transaction into running when done that way. If you're using the running and candidate data stores, EditConfigs are typically done towards candidate. Those will each be a transaction into candidate. Candidate accumulates all those configuration changes, and then later, when you use the commit or confirmed commit operation to transactionally commit the contents of candidate into running, that set of changes going into running is a transaction as well. So using transactions gives us a lot of robustness and stability. In a transaction, they're orderless, meaning it doesn't matter what order the changes are populated into the transaction, the end result is the same. You go from A to B, and all paths from A to B are equal. Also, if a transaction fails, you revert and are at the point where you started. So if a transaction fails, it's not really a rollback, it simply is never activated. You simply stay at the configuration that you started at. Making use of the candidate data store with NetConf allows you to implement a network-wide transaction. As we'll see later when we look at detailed protocol traces, you would use the NetConf EditConfig operation to send changes into the candidate data store and say we're working with 3 devices we need to make changes to. You would do those edit configs towards candidate on each of the 3 devices. Then you could use the validate operation of NetConf, which asks the device to validate the contents of candidate to say, is this a valid configuration if it went live? If that all passes, then you could tell each device to commit to running. And as we'll see with the confirmed commit operation later, that's an even more robust way of doing that commit of candidate into running. The confirmed commit takes that change live. The device is using it. However, when you issue the confirmed commit, you specify a timeout value. For that timer, if it expires before you confirm that commit, the device automatically reverts to its original configuration. So it gives you a fail-safe mechanism. So say, for example, you accidentally disable the management interface of a device. With a confirmed commit, the device will revert to its old configuration, and that management interface will be back in the system. So you can effectively get what we'd call a three-phase commit using NETCONF with confirmed commit. You're doing your changes into candidate, you're validating them, then you're using confirmed commit in order to give you automatic rollback in the event of an error when it actually goes live. The NETCONF protocol has a set of base operations that must be present. Then past that, we'll see there are sets of optional or extension capabilities or operations which may be present, but these base operations we see on this slide must always be there. GetConfig, EditConfig, CopyConfig, commit, discard changes, cancel commit, etc. So the get operation is used to retrieve data from the device. Now you'll notice there are both get and GetConfig. GetConfig will only retrieve configuration data. Get will retrieve both configuration and operational data. In your Yang data model, those determine paths to your data based on the XPath into the data model. So when you do a get or GetConfig, you'd issue the path, which is the base of a subtree that you want to retrieve. If that subtree contains both configuration and operational data, GetConfig will only get the configuration parts of that subtree, whereas get will retrieve the entire subtree. EditConfig is how you make changes to the configuration of a device. It contains, it specifies the target data store you're writing to and also the values to write. And there are some options available for the EditConfig. CopyConfig we'll see primarily used to do things like if you want to make sure the contents of candidate equal running before you start doing things, you'd use CopyConfig to copy running to candidate. Commit is used to copy the changes that are in the candidate data store into the running data store. Obviously, you need candidate turned on, which is this :candidate reflects that if the device advertises the candidate capability, then commit may be used. If it also advertises the confirmed capability, then you can actually do a confirmed commit as well. Discard changes and cancel commit are both only used when the candidate data store is turned on. Discard changes throws out any changes that are in candidate, and cancel commit is used to cancel a ongoing confirmed commit that you just want to end. And then DeleteConfig, lock, unlock, close session, kill session are the other main base operations. Lock and unlock are used to take exclusive locks on a data store because you may not want to allow any other changes to be occurring in the system while your NETCONF system is managing the system as well. Kill session and close session are used to end NETCONF sessions. As we mentioned earlier, NETCONF is transported on SSH and TCP, so it is connection oriented. You authenticate in, you start a session, and you need to be able to end the session gracefully with close session. Kill session can be used as part of management if you need to kill another NETCONF session in the system. So here we see an example configuration sequence. On the left is the traffic coming from the NETCONF client, i.e. the management station. On the right are the replies from the NETCONF server, i.e. the agent in the network element. So one of the first things we see is it's XML, as we mentioned earlier. And we'll see the opening tag is RPC coming from the client, and the opening tag from the server is RPC reply. NETCONF is an XML RPC style protocol, meaning there's remote procedure calls. So in many ways, you can look at NETCONF as a protocol, or you can look at it as a XML programmatic API into the network device. So the RPC comes from the client, the RPC reply comes back from the server. So we see here in the first item, the EditConfig RPC is being sent. We see it goes against the target of candidate, a couple of options, and then in that config section is the actual configuration we're sending with that EditConfig RPC. In terms of what we see there between the config tags of interface, name, IPv4 address, etc., how do we know what the layout of that XML is? What's the schema that's possible there between the config tags? That is where the Yang data modeling language comes into play. Based upon the Yang data model for the specified namespace for interface, that will tell us what XML is possible there for config. The NETCONF agent will verify it against the Yang data model schemas. So we have NETCONF is the protocol and the framing. If you think of what's between those config tags as the payload, Yang is used to specify the possible format of that payload. Now, for this EditConfig RPC, if you notice back on the RPC tag line all the way at the top, on the right in red you see message ID equals 5. When that RPC is sent, if it successfully executes or if there's an error, the NETCONF server in the device will send an RPC reply, of which the RPC reply tag you'll see there has message ID equals 5. And in this case the payload is OK, telling us that EditConfig succeeded in the device. Another example is the second message a little further down, where we see the RPC with a message ID of 6. There we're issuing the validate operation. There we're asking the device, are the contents of candidate valid? What this causes confd to do is run semantic validation against the contents of candidate to say, does candidate contain a valid device configuration that if we were told to go live with it, it would successfully go live. So we ask it to validate. Again, we see the reply to message ID 6 of OK. Then we see the manager issue the confirmed commit, which is the commit operation with the confirmed option, and the device replies OK. We'll look at some more detailed protocol messages as we go through here. Now, as I mentioned, the core NETCONF protocol has a required set of base operations that must be supported by all NETCONF compliant devices. NETCONF also supports optional capabilities that are advertised in those hello messages, and the core NETCONF RFC 6241, which specifies NETCONF version 1.1, has a total of 8 optional capabilities that may or may not be present in devices. Writable running says that the running data store may be written to directly. Candidate indicates that the device has the candidate data store present. Similarly, for the rest of these options, confirmed commit, that is available. Rollback on error, meaning the device can automatically roll back on an error. Saying that the validate operation we talked about on the previous slide, where we could ask the device to validate the contents of the candidate data store. Then startup indicates that the startup data store is present in the device and may be used. URL is a capability to be able to specify, there is some more data available in a file via FTP or other mechanisms, i.e. add a URL. We'll find some more options. And then XPath allows us to filter data responses. We talked a little bit about get and GetConfig earlier. You could normally do a get or GetConfig at a point in the tree and get the entire subtree. It is possible to filter those results, so you don't have to filter them at the management station. There's the idea of a subtree filter that only gets a certain partial subtree of that tree, or you can give an XPath which will filter out and only return nodes that meet a particular criteria. Like maybe I have a Yang list, i.e. a table, and maybe one of the columns indicates a up-down status, true, false. I could specify an XPath filter on a get to say, give me the entries in this Yang list, i.e. the rows in this table, for which the status is marked down, or perhaps false in my model. And that XPath filter filters that out. So effectively it gives a bit of a query mechanism into the data. NETCONF, as we've mentioned previously, is an extensible protocol, meaning new operations can be added to the protocol. You have the capability, people can do this themselves when they're doing an implementation, although with that you do need to be careful because those are proprietary extensions, so both the management station and the device need to understand those capabilities in order to work. However, the main intent of adding this extensibility is that as NETCONF got use in the real world, which it now is getting used quite extensively, we'd learn things and what needs to be added to the protocol, what needs to be modified. So the extension capabilities get specified in this various list of RFCs we see here are some of the ones that have been published. For example, the NETCONF monitoring capability, if present, indicates the items from RFC 6020 are present and available in the system, which includes a Yang data model along with some schemas. For example, the RFC 6020 added a new NETCONF operation, i.e. RPC, that allows us to query the device and fetch from the device the data models of the device without having to load them on the manager. You can define your own. There are a few TLF extensions we've added to NETCONF that can make some things interesting or extend some capabilities, make it easier to do. You can actually learn about any of the TLF extensions that are available and for use in the NETCONF server chapter of the ConfD Users Guide. That gives us a introduction to the basics of NETCONF. Let's start looking in detail at various NETCONF operations and see them in action. First, the hello operation. As we mentioned previously, the hello message is sent simultaneously by both the NETCONF client and server when the connection occurs. Typically, the management station or NETCONF client advertises a minimal set of capabilities because what really matters are the capabilities of the NETCONF server, i.e. agent, in the device. So from the hello operation, it gives us the capabilities exchange, which tells us what NETCONF operations are available to request of the NETCONF server. It also allows the network element to advertise what data models and revisions of those data models are supported by the device. There is also the encoding and framing as a result is specified. As mentioned earlier, NETCONF 1.0 and 1.1 had slightly different framing mechanisms. So here at the bottom of the slide, we see a very basic hello message that is sent. We see the encoding, we see hello, the namespace identification saying for NETCONF 1.1, and a capability that the only capability advertised is the base operations of NETCONF 1.1. This is probably the most basic hello message that can be sent. This slide shows an example of a more detailed hello message. This is a typical hello message that may have been sent from a NetConf server in a device. We see in between the capabilities tags, the capability list. We see base, we see writable running, we see the candidate is supported, confirmed commit, etc. We also see some additional capabilities, which are tailf extensions, but then we also get down to where you start seeing the second from last capability. That is, the namespace there shows example/DHCP module, etc. That's an advertisement of a data model. That is the DHCPD data model in this device. But there is no revision being advertised for that data model. That last capability for IETF INET types includes a revision identifier. You see there the revision of 2010, September 24th. That is the revision of the IETF INET types data model that is supported in the device. So if you follow and implement the Yang revisioning guidelines for your data models, not only can you identify what data models a particular device is using and supports, it also can identify the revisions of those data models which are present and available for use. Then also you see the session ID. That is the session ID assigned by the NetConf server for when this client attached. So if for any reason you need to refer to this session later on, the session ID comes in that hello message back from the NetConf server. Next, the GetConfig operation. The GetConfig operation is used to read configuration data from the network element. There are some options that can be used with GetConfig. There's subtree filtering and XPath filtering. We'll see both of these in action. In fact, one of them we'll see here right now. This first RPC that's shown here is a GetConfig. Then we see the source. So the source attribute of GetConfig indicates running. So we're doing a GetConfig from the running data store. Again, what tags or attributes can be within, say, the GetConfig operation. Those are fully spelled out in the relevant sections of the RFCs. Now here we see, after the source tag, we see the filter tag. This can be used to implement subtree filtering. In this case, the namespace specifier on the filter operation is referring to a data model in the device, which happens to be a AAA data model. And the filter tag of AAA, if you looked at the Yang data model for this data model, you'd see at the top of that data model a container called AAA. So this filter is written with the basis of knowing the data model and effectively returns that entire namespace, assuming all of that model is contained under that AAA tag. Here's a potential reply that could have come from that GetConfig that was sent by the client from the server. Again, we see it starts RPC reply with a matching message ID, and then the data tag is part of the framing. So this is the data in reply to that GetConfig. The payload here between the data tags, that XML data that is there, that layout or schema of that XML is determined by the Yang data model. So we would have seen a data model that was container AAA, container authentication, list users, and then some number of user entries within that user's list. And then each user entry, various data there. But this is how a data return looks like in response to a GetConfig for NetConf. EditConfig, as mentioned earlier, is used to make a configuration change to the device. So here we see a EditConfig RPC going into the device. The first thing we need to specify is target. Which data store are we modifying with this EditConfig? In this case, we're writing directly to the running data store. So target is running, and then again, config is the payload. So between the config tags, that DHCP, default lease time, that is determined by the Yang data model corresponding to the appropriate part of the config that we're changing. That model is identified by that namespace attribute on the DHCP tag. And then we see a reply of this edit succeeded, so the NetConf server sends an RPC reply of OK. The CopyConfig operation is primarily used to copy configuration between data stores. Very commonly, it'll do something like CopyConfig from a source of running to a target of candidate. However, it can also be used if the URL capability is supported and enabled to copy information to a URL or from a URL. So here we see an example. The client has sent a CopyConfig RPC to the server. The target of this CopyConfig is running. So that is where the copy results will go to. The source of the copy here is specified as a URL. So from this URL, that file will be fetched from that URL, and then it will be applied into the running data store. So the contents that are being fetched would follow the schema of the data model appropriately. And again, if it succeeds, we get the RPC reply of OK. So far, we've only seen OK replies. If there was a problem, the RPC reply would have the error tag, and then that error tag could contain additional detailed information about the error. The DeleteConfig operation is used if we want to delete a complete running data store. In other words, the complete contents of a data store. It cannot be used against the running data store. You may not delete the entire running configuration of a device with this. Most commonly, it can be used to empty out startup or candidate, but you simply issue the DeleteConfig RPC along with the target data store to apply that operation to. Lock and unlock. The lock operation is used to take an exclusive lock on a data store, and then unlock releases it. Many times in NetConf interchanges, you will see an interchange where the manager will take locks on data stores, do some number of edit configs to them, and then eventually unlock them. This is just to ensure consistency of the configuration of the device so that someone else may not be changing configuration in the middle of your sets of configuration. It's just a way to ensure additional robustness. So lock typically only has the target attribute of which data store to lock, and you'll receive the reply of OK if it succeeds. The get operation is used to retrieve both configuration and operational state data. It works much like GetConfig. However, where GetConfig will only return data items which in the Yang data model are declared as config true, i.e. meaning they're configuration data, Get will return both config true and config false items from the data model. So here we see an example of the Get. The Get is applying a filter of type subtree. What this means is we're not going to fetch an entire namespace contents. A namespace, remember, is a tree or hierarchical shaped because we're in the XML world. We want to, in this case, retrieve one subtree of that overall tree of the namespace, so a subtree filter is used to specify that. So if we went into the data model that this get operation is written against, we'd see the structure reflected here between the top tags, and this tells us to get just the subtree for the ETH0 interface. And on the right side, we see a potential reply for this get with the subtree filter, and the structure again of that reply is driven by the Yang data model, and then the values such as if name, if in octets, etc., are driven by contents of the database in the system or the data store in the system. The netconf close session operation is the way to gracefully end a netconf session. Of course, you could just drop the SSH connection, and of course the session will end, but if you want to gracefully close it, you use the close session RPC, which typically has no options on it. Kill session allows you to disconnect another ongoing session. It will release any locks, abort any confirmed commit related to that session. So you're typically not killing your own session. If it was your own session, you'd use close session. Kill session can be used to kill off another netconf session. Perhaps it's hung, for some other reason. It's not an operation you see typically used, but it is available. So that takes us through the core base operations of the NETCONF protocol, typical operations that any NETCONF server in a NETCONF-enabled network device would support. There are also optional NETCONF operations that are available. The availability of those operations is indicated from the NETCONF server by the capabilities that are advertised in the hello message. So if the candidate capability is advertised in hello, you have both the commit and discard changes operations available. Similarly, if the validate capability is there, the validate operation is there, etc. through the various operations here. So now that we've looked at various NETCONF operations in isolation, let's bring it all together and look at an actual use case of a series of NETCONF operations being used to actually do something. So in this case, we'll look at VPN provisioning. It could be anything. The whole idea here is to look at the typical life cycle of a NETCONF session actually doing something on a device. So in this VPN scenario, we assume we have some number of routers or other equipment. There's a management station that connects to all the devices, and we need to set up a VPN between two customer sites. So we need to do a network-wide transaction because there is no one router that both sites hook to. So we need to set these up on a series of routers and simultaneously. So first, we'll look at talking to what we'll call router west. Here we will show some identification in this series of captures that indicate by those series of greater than or less than signs where the traffic's going to. So this hello message is going into router west, and that second hello message is coming out of router west. So as we look through these traces, you can tell which direction the traffic's going in. So here, the hello exchange, the top one, is coming from the NETCONF client in the management station being sent to the server in the device. Since the capabilities really need to be known by the client at the management station and not so much down at the server, the client usually advertises minimal capabilities in its hello message. Here, it advertises just NETCONF 1.1. Coming up from the NETCONF server in router west, its hello capability is actually very small, but for the purposes of demonstration sufficient. It supports 4 capabilities: the NETCONF 1.1 base capabilities, the TailF extension actions capability, and then 2 data models, the AAA and an example data model for the Quagga open source routing suite. And we see we're identified as session ID 4 here. So we've connected, we've sent our hellos to advertise our capabilities, and now the session's up, running, ready to do management operations. So first, we want to make sure the device has no pending changes. So we send the RPC discard changes to the device. It discards any changes it may have in its candidate data store and replies, OK. Then we take a lock on the candidate data store because we don't want anyone else making changes while we do. So we send a router west a lock against the target of candidate to take an exclusive lock on the candidate data store. We'd be doing similar interactions to other routers involved in this scenario. So we've connected, we've discarded any changes that may be there, and now we take a lock. And again, we simply see a reply of OK from the device. So, since we're going to be modifying candidate and then committing it to running during this session, we also take a lock on running. So we see the RPC lock, target, running, and the reply of OK. Here we want to ensure that candidate matches the current contents of running and that there is no mismatch. So now we issue the CopyConfig RPC with a target of candidate and a source of running. This will cause the device to take its current running configuration and copy it into candidate. This way, as we do edit configs against candidate, we know that only the changes we're making will be reflected in the final running configuration when we commit it from candidate to running. If we didn't do this, there might be a danger that there's some previous changes that had been made to candidate that we don't know about and haven't been committed to running, and we've added our changes, and those dangling changes may get accidentally copied to running inadvertently. So making sure that they are in sync, simply make sure we don't make a mistake in configuring our network. So copy the config from running into candidate for a known starting point. By the way, that may not necessarily result in an actual copy on the device depending on the underlying implementation. For example, CompD has optimizations in place that may not need any of the data to really be copied. It may be just a logical copy. Next, we want to send changes to the device. So again, we use the EditConfig RPC to make changes. So we're doing, in this case, a target of candidate for these changes. And then under the config, the rest of the things, the XML tags that have the Quagga prefix on them, are referring to the data model for Quagga and are determined by that Yang data model. So the edit config is sent, and we didn't show, but the device would have said RPC reply of OK. Next, we have the validate operation. After we've done the series of edit configs against candidate, populated all the various changes we want there, we can ask the device to validate those changes. Without taking them live, all semantic validation is done, checks of Yang must statements, etc., invocation of additional validation logic, whatever the device needs to do to validate the potential future configuration that's stored in candidate. The device does the validation. If everything passes, that RPC reply of OK will be returned. The device doesn't necessarily know what will come next after the validate. You could do some more edit configs, another validate, and a commit. It's really up to you. These are all just building blocks. Remember, NETCONF, while it's a protocol, is also an XML API that gives you programmatic control of the device as well. We've done our changes. We've asked the device to validate it. Everything's fine. So now we issue the commit operation. In this case, if we just do commit, this is a transactional commit of the changes that are in candidate into the running data store and taking them live. So at this point now, they're in the running data store, and this configuration is live in our device. We've made the changes, we've taken them live. Now we simply unlock the data stores we had previously locked. So we unlock candidate and we get a reply of OK, and then we'd unlock running. So we looked at doing this using the standard commit operation. Something that gives us more power is the confirmed commit operation if the device supports that capability. A confirmed commit takes changes live, but there's a timer running that if you don't confirm those changes before that timer expires, the device automatically reverts to its previous configuration. This is a very powerful tool for implementing network-wide transactions, because if we're using confirmed commit, we can do edit configs to the various devices involved in the scenario, and then we can do confirmed commits to take it live on all the devices. But if we get an error occurring on any of the devices, by confirmed commit, we can cause the device to automatically revert back to its old configuration and cause the transaction to fail. If we had done a commit, instead of confirmed commit, we'd need to go back and do edit configs to devices to take them back. So here we see an example of a commit RPC. So we'd have the commit RPC with the confirmed option. That makes that commit a confirmed commit. There's a timeout specified. The device says OK. Now, what if something went wrong? One of the devices disconnected. Here we showed the use case talking to router West, but we may have been talking to 2, 3 more routers as part of this, doing similar operations of the connection, the capability exchange, the locks, the edit configs, validates, confirmed commits. If with the confirmed commit, if something went wrong, and we've done a confirmed commit, maybe it succeeded here on router West, but it failed on router East. In that case, for the confirmed commit, if you simply disconnect from the device knows it's never going to get the confirming commit stop and say everything's fine, stop the timer from running. If you disconnect, the device will automatically revert to its old configuration. So say one of the other devices disconnected or failed, gave us an error return, we simply, with the management station, drop our NetConf connection and reconnect to the devices, and that'll cause them to automatically roll back. That's the true power of confirmed commit for implementing network-wide transactions. So, very common NetConf use cases, network-wide transactions as we've discussed here, potentially applying and testing a configuration. Put it in candidate, validate it, see if it validates. If it doesn't validate, we may end up having it rejected, but we've had a chance to test it. The rollback when a device goes down, especially with confirmed commit. Very, very, very powerful tool to use in network management. You could do other use cases. You could implement a transaction that's network-wide requiring all the devices to be there. You could implement a backlog transaction for your network, meaning say I want to update, a DNS server address across all my devices. I could implement from my server a backlog transaction. I make that transactional change out to all the devices I can reach right now, but maybe there's some devices I can't reach. I create a backlog of changes, and later on when I can reach that device, I could send it there. I could use NetConf for synchronization. In my management station, I have a database of my network configuration of all my devices. How do I know that someone hasn't gone in locally into a device, made changes, and not done it through the management station? I could use NetConf to do a GetConfig from a device, get just its configuration, compare it to my stored copy, or maybe I can do some optimizations to prevent moving the data. Maybe I can check some sort of transaction ID or that. But these are all different types of use cases that have been implemented using NetConf, because again, NetConf isn't just the protocol, it gives you programmability of the management of your network devices. So that finishes up the NetConf tutorial. I hope you've learned something here about NetConf. and you'll go off and look through some of the RFCs and learn more about it, and look forward to having you join me in some future training modules around ConfD.